Hello and welcome to another episode of the Oxford Online Maths Club. It's great to have you with us. My name's James. I'm going to be running today's session talking about some maths that I've been thinking about recently. I'm joined in live chat by, well, no current students at the moment, I'm afraid. They're all getting ready for their exams quite soon. But I'm joined in live chat by you, people watching live. Who's currently here? We've got George, Rebecca and Athena have found the chat again. Thanks for hanging out just before we go live. They all say hi. Also, a person with username Mu, the Greek letter that's a bit like M. I'm well, thanks. Thanks for asking. I hope you're well too. I'm going to try and type some replies over in the live chat as well, but my spacebar has broken. So if you get a kind of particularly breathless, enthusiastic, all strung together response from me, then that's just because my spacebar's not totally working brilliantly. Shout out hi to Joe, hi to an anonymous person who reminds me that if you join our live chat, you don't have to sign in, you don't have to set a username, you can be anonymous if you want to. It's one of the reasons that we're using this live chat rather than the kind of YouTube infrastructure googly stuff. That's over, by the way, I sometimes forget to say this, that live chat's over at www.slido.com/OOMC. I think there's a link down, there's a link down there somewhere, isn't there? Right, okay. And somebody's asked an admissions question. They want to know, can I get into Oxford without the maths test? The maths test that we're all clear is a maths admissions test that Oxford gets all of the maths applicants to take. Very occasionally somebody can't take it for a good reason, but usually 99.9% of the people who just study maths at Oxford in recent years have taken the MAT. So, I mean, if you don't do maths, then maybe. Hi Alice, hi Reese, hi to an anonymous person who likes Slido. Look, this is the sort, here it comes, a bit of lag. It's just a bit, there it is, Slido is best, says an anonymous person, that's what we're looking for. Hi says another one. Jonty says they're looking forward to this one. I can't remember what I put in the title for this one. Something about complex numbers, right? Something about complex numbers. I'm stalling a little bit for time while I let people arrive. I've worked out that people arrive over the first 5 minutes. I think people have learnt that the first 5 minutes is me explaining the Slido. Rose says, how am I? I'm all right. Been thinking about some maths problems. It was a bank holiday weekend recently, but I've been doing some teaching as well, which is always fun. Teaching this close to exams is sort of quite revision focused. We do some of our tutorials, small group teaching, which is just sort of revision mode, checking we're revising all of the things from over the year. So I've been doing that with a few of the Oxford students. Hi to Sebastian and Jamie. Okay, I think we've got people through and people have found the live chat. Woo says Maximus and hi says Zach. People are still finding this Slido. Rose likes last week's geometry one, which reminds me that previous episodes are available on the Maths Club website. I should write this script up, right? I should write the script up of what I say at the start, because this is like the 20th one and I still haven't quite worked out the script. Previous episodes are available at the Maths Club website, which is maths.ox.ac.uk/r/club. Lots of them have got current students, a range of people on talking about their favourite sort of maths. As we get close to exams, it's me. I've got a couple of our graduate students coming up as well in the next few weeks. But today, just me. I'll do the coming up, then I'll answer that question that's just appeared underneath my face. How do I do the coming up? I can't even remember. You wouldn't think that I did this every week, would you? Right, okay. Coming up today, we've got some integration. People might have remembered a couple of weeks ago we did some integration with a DT. It was really good fun. I've got some more stuff about integration today. I'm going to combine that with complex numbers, which we've talked about a couple of times on the live stream. I'm going to try and merge those things together. Later on the stream, my computer is going to explode because I'm trying to make it do some bits and pieces. I've done some coding. And I'd like to show you what I've built. Okay, Flynn's got a guess. Complex numbers technically are the combination. The calculus is going to get messy because there's a couple of variables. Yeah, complex numbers are brilliant like that. How many exams do you do? Was the question that an anonymous person asked. I'm going to try and mash together the kind of people asking questions with the maths I've prepared. They do some exams at the end of the year. In first year, they've got kind of 5 papers. Later on, they do more papers that are a bit shorter on a variety of options. But no, my first years have got 5 exams coming up. They're a couple of hours long each, over the course of a week. And they've done a few exams, kind of practice exams, at the start of second and third terms, just to practice things from the previous term. Right, okay. Let me tell you roughly what we're going to do today. We're going to do some integration. I just did this. I was on the slide. Right. Further reading. I really should write that script of things I say at the start of every episode. You could probably do it better than me, because if you've seen this, then you know what I'm going to say. Further reading is posted on the website maths.ox.uk/club. Every Friday we post bits and pieces related to stuff from the previous day's live stream that we forgot to say live, or stuff that we should have put into the live stream but didn't make it into the live stream. Okay, so integration. Quick recap of something we saw in Aditi's integration live stream a couple of weeks ago. We saw that if the derivative of big F is this function little f, and if the functions are nice in some sense, I think one of them, we define things like continuous and differentiable. I'm just going to abbreviate today all of the stuff about continuous and differentiable. I'm going to abbreviate that with the word nice to just mean, well behaved, nice functions like that, things that do nice properties like that. If you're interested in the details of what nice means here in quote marks, then a couple of weeks ago we did a live stream looking at what do you need to be able to say that you have this derivative fact, you get an integral fact, you get the integral from a to b of f of x with respect to x is equal to the difference in the end values of big F. Okay. Just going to fiddle with a setting, sorry, which I can't talk and change the setting. There we go, fixed. Right, good. There we go. It's got my pointer. My pointer is lined up with where I expect it to be now. Good. Right. Okay. We saw this integral of small f of x equal to difference of big F's. In fact, this is the fundamental theorem of calculus in one of its many forms, and you use this all the time when you're integrating functions. You might see an integral that you want to do, and then think in your head of a function big F, capital F, that satisfies the derivative is equal to small f. Aha! If you can think of that function, then all you need to do is to plug in the values at the endpoints. Sometimes people write this thing as sort of f of x, big F of x, b and a. Maybe I shouldn't have used capital F and lowercase f at the same time on the same slide. Never mind. Okay, that was the fundamental theorem of calculus for functions taking real number inputs and real number outputs. Today, here's the twist. What about complex numbers? So we're going to put some complex numbers into this picture and see what that changes. See what's the same and what's different. Okay. It's worth. So before I tell you exactly what we're going to be doing, it might be worth kind of staring at this and thinking a little bit to yourself. How would you combine together complex things like integration, like on the screen, and stuff you know about complex numbers, if you know anything about complex numbers? I suppose this is one of those live streams that uses a further maths fact. Maybe, so this is kind of a chance to practice inventing mathematics. It turns out there's a couple of ways to get complex numbers involved. Here's a really big complex function. Complex functions are usually written as a function of z, where z is that complex variable. I mean, you can call these things any letter you like, but normally people write them as function f for function, z for the input variable. So you can have kind of complex output of your function, and that's kind of quite nice. That's quite that's kind of nice and easy-ish to deal with. If your function just takes in real numbers and it spits out things that are multiplied by I, or things that are like 3i x squared plus 2 or something like that, turns out that that's all very nice and it's easy to work with. Complex outputs, turns out that's fine to deal with. You can set up integration in the same way that you normally do. You have these real inputs, complex outputs, that's all fine. But as George says, we're going to do something with the Argand diagram. So if you've got an input and then a complex output, you could imagine the output being somewhere in the Argand diagram. Things are going to get really complicated if we start thinking about complex input. So I guess this is one reason to use Z instead of X, to really stress that we're using complex inputs. So if your inputs lie in complex numbers, then your function can be quite complicated. It's going to have different values. Remember what a function is. A function is something that takes a value for each possible input. It's going to have a value for each complex number that you put in. So I've kind of got this big F on screen just to really stress there are kind of two changes that we're making. One is that the outputs can be complex numbers, and one change is that the inputs can be complex numbers. Yeah, how are we going to do this? So there's a challenge to do things graphically, says an anonymous person below. It's really good. Because our input is now kind of two-dimensional and our output is sort of two-dimensional as well, it's starting to feel like I want a kind of 4D graph that's got kind of inputs and outputs. And in practice, nobody really does that. Nobody tries to draw 4D graphs. Are we going to do areas in Argand diagrams? Yes, we're going to go to an Argand diagram, I think. So Argand diagram is just going to mean, if you haven't met this before, Argand diagrams is just a kind of map X and Y. The X and Y axes are the real and imaginary parts of a complex number. We're going to look at that for the input. Ooh. Is this going to be complex analysis? Yes, but I don't expect that to mean anything. Right, okay. There's some good suggestions coming in. I also like that people are taking kind of constants as their usernames. Register quickly for a good constant. E says, for a complex integral, could you look at extending a new axis from the origin and look at the volume of a function? So people are kind of thinking about this higher dimensional sort of thing. I suppose what I want to think about is integrals that look as much like this as possible. So integrals that look like this, where we have a kind of starting point and we have an end point, and we're integrating values of the function. So this is kind of what it feels like to invent mathematics, I suppose. We're going to try and make something a bit like this, but we're going to put some of these complex functions in and just try and replicate that as much as we can for complex numbers. You with me? We're kind of feeling out what we can do and what we can't do. And at some point my computer's going to explode. Okay, so what would I want? I'd want A and B. I suppose my function is now f of z, dz. I'd want this sort of integral to mean it's from A, so this is sort of my starting point, and this is sort of my end point B, f of z dz. Now, normally integration, I suppose, the best way to imagine integration I find is to imagine moving along the real line from A to B, so from A to B, and looking at the value of the function along the way. And okay, in the real world that looks like an area under the curve. If you take the value of the function, look up the value of the function, and do your integral by just adding up as you go from A to B, adding up little bit of dx, little bit dx, a bit of function height. This is a bit like the pictures Aditi was drawing last week, and a little bit like the kind of rectangles to approximate a curve kind of idea, rectangles to approximate an area kind of idea. If I take these values and I add up little contributions dx times the value of the function, that's a good kind of mental image, because then I can kind of do something similar over here. Okay, bear with me. A and B, like Flynn says, are going to be complex limits, so they're going to be points. Let's see if this is the Argand diagram from the real parts and the imaginary parts of my input. This is my Argand diagram. Where are A and B? Well, before A and B were just points on the real line, but now A and B could be points in this Argand diagram of inputs. And then to do our integral, we need to go from A to B and add up along the way, add up contributions from what the value of the function is along the way. Okay, I'm being very careful, but I think Zach's got to this 4-dimensional graph idea as well. I'm being very careful, but I think we can do something a bit like we normally do for integration. This idea of having lots of little contributions that we add up to say, go from A to B, and along the way, kind of just add together the values of the functions you see, multiplied by some little dz for how much z is changing as you change z from A to B. Now there's an elephant in the room, there's a kind of big problem with this. Let me show you what the big problem is. There's more than one way to get from A to B, as I think you know. Right, so you could start from A, you could go over like this to get to B, or you could start from A and you could do something like this to get from A to B, like this. There's more than one way to get from A to B in the Argand diagram. Let's be really clear. This picture with the blue and purple arrows in is just looking at how Z changes. Z's my input to my function. It's just looking at how Z changes as I go from A to B. And in the real world, going from A to B, there's only one way to do it. You start at A and you go through all the numbers in between. In the Argand diagram, it's sort of not clear which numbers are in between. Yeah. So Rose says, what will the area be when it changed? And Zach says, is it best to choose the straight line from A to B? And we could go down that route. Maybe it does matter. Maybe it matters. You know, those are different routes. They've got different things added together. And Zach says maybe we should just use the straight line. So we've got this kind of point in our theory now where if we're inventing this mathematics, then we can go down different routes. Zach's theory is that the next thing to do is to put a straight line from A to B and say that's what I mean by the integral from A to B. Rosa's idea is actually it might matter what path you take from A to B. Maximus has asked that as a question. Sorry, there's a bit of lag between chat and the screen. And I think it absolutely could matter how we get there. Does it matter how we get there? It's a very natural question to ask. What mathematicians, the way the theory goes in textbooks, and it's not the only way to do this, but it's to talk about, to give these curves a name, and to talk about the integral of f of z dz along the curve gamma. So this means, I don't know why gamma is the name that people give to curves, but bear with me. So this is along the curve gamma. So just in case it matters, maybe it'll turn out not to matter. Maybe not. Maybe this concern doesn't matter. But just in case, when we set up our integral, what do we mean by integral? We're going to specify the curve gamma that we're integrating along, which, just to say it one more time, we're not calculating the kind of area underneath this purple curve. We're not working out kind of areas in the Argand diagram or something like that. This is just how we're changing z to get from A to B. We're doing changing z along some curve. Yeah, okay. Along the way, we're going to add together values of the function. Flynn says, like the real line, we just use a straight line, which is a theory. Was that Zach's theory before, or was that Flynn's theory before? I can't remember. People seem to be quite in favour of using a straight line. We're going to explore the theory a little bit. Just, if you want to use a straight line, bear with me. We're going to discover something really cool, and then you're going to turn out to be kind of morally correct, I think. But save that high ground for a minute. Yeah. So E has got a comment: potential routes above and below. So we do have to choose a route. I think there's something weird in quantum theory that people might have heard of where you consider all possible routes. We're not doing anything crazy in quantum today. We're just going to say, well, let's choose a route and see what happens along that route. How are we going to approximate the infinite number of points between A and B? I guess I'm going to take the route between A and B and I'm going to do something a bit like this to split it into finite pieces and to add together some little finite pieces, if that makes sense. Approximating the integral is something my computer's really good at. In about 30 seconds, I'm going to give this to my computer and we're going to play with this and see what happens. Right, okay. Ah, right. So 196883, that's a cool username. 196883 wants to know, is that property that we saw before, is that going to hold only giving one value, doesn't matter on the endpoints? We're going to find out. Okay, right. I think it's time to show you my incredible code. Right, okay, what am I going to do? I'm going to close PowerPoint to try and preserve my computer. I'm going to open up the code interface. Everyone cross their fingers. Okay, right. Let me explain what's going on here. So, it looks a little bit janky, sorry. So I've picked a function. I thought I'd help my computer out. I'll name a function. I've gone for f of x is 1 over x, which is quite nice. It's got lots of, you can differentiate 1 over x because it's x to the minus 1. You can differentiate it, it's nice. Or I suppose it's not nice when x is 0. So if x is 0, this is pretty bad, 1 over x. But otherwise, 1 over x, lovely function. I've put a red cross at 0 to remind myself, don't go to 0. We're going to do an integral. I'm going to get my computer to do the integral, but don't go to 0. Okay, so on the left here, I've got a bit of Argand's diagram with points A and B. And we're going to try and integrate from A to B. My computer's going to do all the hard work, adding together little bits of numbers. I'm going to tell it where I want the path to be. Okay. So first up, well, what happens is it's got kind of crosshairs, and when I click, it's going to draw some lines, a bit like this. Okay, right, okay. So this is the idea. I'm going to click, and it's going to draw some lines and integrate along that curve. Let's do a bit of a sort of curve like that. Okay, I'm going to get from A to B, and once I get to B, it's given me its calculation of the integral. Did you see how, as I was clicking, it was adding on, the number was changing. It was adding on new bits and pieces onto the integral as it went along a little bit more of that curve. It's not a very good curve, is it? I suppose it's got lots of sharp corners. Hopefully they don't matter. They don't. Yeah. Oh, okay. That's a good idea from Blah. Okay. So I've integrated from A to B along my choice of crazy curve like this, and I've got the answer. Kind of 0.35 plus 2.4-ish. Okay, this is a complex number as my answer. Complex outputs. Complex inputs in the picture, complex outputs as numbers that my computer's adding together for me. Okay, so that's along that path. Let's see what happens if I restart and if I do what Zach and Flynn want, which is just a straight line. Remember that number, it's about 0.35 plus 2.4i. Okay. Right, you with me? We did it. We've got my computer to add together some numbers. It's incredibly janky. Please don't look too closely at it, especially this UI element that I'm about to click on. Seriously, like coding up getting it to do the integration, easy peasy. Getting it to display the function nicely and getting it to have these pink buttons I can click on, super hard. Right, okay. Reset. Oh, look at that. It's reset. Okay, we're going to try what Flynn said. So if I just click on B, it's going to go straight from A to B and just work out the contribution along that straight line. Okay, so if I do that, aha, something interesting's happened. So it's just done it all in one contribution now, along that straight line. What it's actually doing, when I click, by the way, it's working out, for lots of points along that line, it's working out the contributions along that line. So it's kind of walking in that direction, checking the value of f as it goes. Okay. So I'm taking the integral of the complex output of the function. I'm integrating f of z. Oh, I've written it as f of x on there. That's annoying. I should put z's on. Okay. Have you spotted what happened? So it did one straight line, and look, the answer is 0.34 plus 2.4-ish I. It's about the same number. Right, my computer's doing some approximations and my code's not great. I'm going to claim that's the same number. Am I going to get away with that? Yeah, so I didn't say that very clearly, did I? I'm going to try saying that bit again. It's drawn one line segment, but you get more accuracy when you do an integral. You get lots of accuracy if you use tiny rectangles. this is like if you had to approximate a normal real integral, then instead of doing one big rectangle, you would do lots of little rectangles. So what my code's actually doing behind the scenes is it's drawing one line segment, but behind the scenes it's doing lots of little steps along that line. So every time it does a little step along the line, it adds on another bit to the integral, like having another very narrow rectangle in the area picture. Although I find that thinking about rectangles and areas is not super helpful because everything's in 4 dimensions now. So thinking about 4 dimensions is pretty hard. Zach spotted it, almost exactly the same number. Yeah. Flynn says it doesn't matter. It looks like it doesn't matter what root I use. Let's try some more. I'm going to try some more and see if we can get that going. So if I go over here, so last time I went kind of above. If I go over here and come in from this side, aha, the integral again is 0.34-ish plus 2.4. That's kind of nice, 2.4i. That's kind of nice. It's kind of about the same number. That's brilliant. Okay. Let's try going over this side instead. Sort of a sign that my code's working, by the way, which is always nice. So if I do a nice curve like this, oh, sometimes it does that. I don't know why. So this curve's gone way off to the left because my mouse got distracted. And the integral's still 0.34 plus about 2.4i. That's kind of good. It looks a bit like whatever path I use to get from A to B, maybe it doesn't matter to the answer. Would it be possible, so yeah, E, that's a good idea. Would it be possible to draw the function of the points along the route? That's a really good idea for a plot, and see how it varies across different routes. So on different routes, you get different values of the function along the line. The values of the function are still complex numbers. So it's not easy to draw that picture because the output is complex as well. Okay, but I think people are getting to this looking like looking pretty good. Somebody wanted to go in the opposite direction to start off with, so that's all right. Let's go. Oh, I've kind of messed that up. Let's go over here. Rebecca says, what if we go on the other side of the origin? Okay. To B. And I get 0.34. Ooh, minus 3.9i. What was it before? Is it sort of plus 2.4i? Somebody wants me, if the path crosses 0 plus 0i, then things go pretty badly wrong. Because my poor computer tries to do 1 over 0 when it works out the function at 0. 2 rules of the live stream are don't swear and don't divide by 0. So I'm trying to avoid the cross so that my computer doesn't divide by 0. Okay, that's kind of interesting. It was plus 2.4i before, and now it's like minus 3.9i. That's a bit different. Maybe I just screwed up. Let's try... Screwed up doesn't count as swearing. Let's try a different path. And then up to be like that. Yeah, it's about 0.35, kind of same, but minus 3.9i. That's a bit weird, isn't it? So there's something weird going on when, to start off with, it looks like whatever path I used always gave me the same answer when I integrated from A to B. But now it seems a little bit subtle. If I go on the other side of the origin, it's sort of, it's different by, what's 3.9 plus 2.4-ish? That would be about 6.3, wouldn't it? About 6.3 difference. Okay, and it looks like it does that wherever I go around here. So even if I go all the way around here. Add up. Yeah. Any other suggestions of paths we should try? What are the coordinates of A? Somebody's asked. There's about 1.5 plus 0i, I think, for my initial starting point. Yeah, the graph in 4D is really bad near the origin. It's it's not continuous. So is this a bit like integrating real functions? I'm going to pass on this question about real functions. I think it's not quite like that, but I want to not think about areas too much. Okay, so I'm going to try something different. Can you go around the negative side without going around the origin? That's a good experiment, right? Okay, this chat message from Sebastian. Okay. Oh. Yeah, the real value. So the real value, the observation, I guess, that someone's got here is that Maximus has got the real value is about the same, but the I value, the imaginary part was different. Okay. So there was a suggestion there if I go into the negative half plane, but don't go around the origin, well then I get 0.34 plus 2.4i. That was the original value again. So it's sort of not quite that. Let me try and do, if I do this, so if I come up to here, and then just go around the origin, and then do something like this. Oh, that's the one with minus 4i. It's getting a little bit tricky. It's almost like, yeah, so here's someone saying, it's almost like if you go anti-clockwise it gets one answer, but if you go clockwise it changes the answer by 2 pi I. Can you cross over the path in a circle? Yeah, and somebody wants to go round the origin twice. Let me show you another path, just because I'm getting bored of thinking about this number 0.34 plus 3.9i. What I'd like to show you is a loop that starts at A and ends at A. Okay, maybe it sounds a bit stupid, right? Because if it starts at A and ends at A, that's like integrating from A to A. And if I integrate from A to A, then shouldn't that be 0, right? Big F of B minus big F of A, if B equals A, then shouldn't that be 0? And in fact, if I do a little loop over here, so if I integrate from A to A, I get basically 0. Oh, that's not as close to 0 as I would have liked, but it's kind of close to 0 if I go around. Don't look too closely at those numbers that are definitely exactly 0. So if I do a little loop, how do you get that? If I do a larger loop around the origin and come back to A, then I get, aha, looks a bit more suspicious now, doesn't it? So I looped around the origin going clockwise, and I've got minus 6.28i. Aha. So George's theory is that this is something to do with the third quadrant. George, let me try and show you. Oh, I hate it when it does that. So there's something over on the left that sometimes borrows my mouse and just goes woof over there. Okay, third quadrant. Alright, so if I don't go around the origin, then basically 0. That's minus 0.0000. Actually, not that many noughts because my code's not that good. So we are seeing some patterns here, and I guess I've got a question. I'll put it as a poll. Yeah, here we go. This is a poll that I set up before. I'm going to integrate. Here's what I'm going to do. I'm going to integrate from A back to A, and I'm going to go around the cross at the origin, anti-clockwise, twice. So this is the thing people have been asking for, where I go around twice, looping around, and get back to A. What do you think is going to happen with that one? Ooh, and the options are 0, 2i pi, 4i pi, minus 2i pi, or something else. So I'll just do a few more while you're voting. This is really confusing, by the way. So if I go around the origin like that, then I don't get a 0, I get minus 2 pi I. Oh, I suppose by putting the poll up, I've admitted that 6.28 is pretty close to 2 times pi. Okay. Let's do a warm-up one. So that was going around clockwise. If I go around anti-clockwise, going around the origin and getting back to A, then I get plus 6.28, that's about 2 pi, plus 2 pi I. That's a bit weird. Let's go for it then. Let's have a quick look at the poll for posterity on the screen here. Oh, this is really broken. Oh no, here we go. Voting. Oh, that one's winning. Okay, so I'm going to go anti-clockwise twice. So look at that integral go. It's already up to about 4.6 in the imaginary part. We're going round again. So I can cross the path over if I want to. I'm going to go round again. And as I get round again, oh, it's enormous imaginary part, like 12. What is that? 12.5 times I. That's about 4 pi I, which is kind of amazing. So people who voted for 4 pi I, yeah, that's a pretty strange thing. Yeah, so maybe, like path, almost like path independence. People are trying to come up with words to describe what we're seeing, which I love. Like path independence. So path independence, I suppose, would be if the path doesn't matter, but the path does matter. So orientation of going around one way is kind of different from going around the other way. So by the way, the reason, so earlier on we were talking about definitions of integration and how if you invent a kind of integration where you think about different paths, then you go kind of open to this kind of discovery that, oh, this is weird. It kind of looks like it almost doesn't matter, but then sometimes you go around the origin or something and you get a different number. Zach and Flynn earlier proposed a theory where you just go in a straight line, and that theory works. It's kind of quite elegant in that it doesn't have this observation. If you just go in a straight line, then you don't do any looping around. You don't do any looping around origins or things like that. Right? Is it a little bit like modular arithmetic? There's definitely something kind of 2 pi I, 4 pi I integer multiples going on. Can we do it with B? Yeah, should we try B? Oh, I have to start from A because of how I've coded it. Sorry. The real part though, yeah. So love this observation. Real part doesn't seem to be playing any of these games. Real part's just being nice. It's got back to 0 here. So the integral is, and there's a prediction. I love. There's a conjecture. Look at this. The same regardless of path, plus or minus 2n pi I. That's true. That's a fact. Reminds you of quadratic residues. Quadratic residues from episode 0. Ah, that's a throwback. Yeah, let's try it with a different function, says 1968883. That's a good idea. Here's my next one. Okay, this is 1 over x squared minus 1. So this function has got 2 points that are no good. It's got points at 1 and minus 1, where, x squared minus 1 is 0 there, so I should not put in 1 or minus 1. Don't divide by 0. Okay. If I want to integrate from a to b, though, I could do something like this along this path. I get a different answer now. I'm integrating a different function, so I'm going to get a different answer. The sort of values that my poor little computer is adding together, the values are different, so I'm going to get different answers. Okay. Yeah. Oh. Okay. So changing paths. Okay. So this is nice. If we go from a to b, we get some integral. In fact, maybe for this one, I'm just going to look at integrating from a to a. I don't like memorising the numbers, to be honest. Whereas when we get back to a, it's really clear if something weird's going on, because if we don't get 0, then we know something's going on. Okay, let's try a very small loop over here just to check what's going on. So integrating from a to a, basically 0. Okay, looks like that thing we saw before for the other function of integrating from a to a, run a tiny little loop, still get 0. Okay, 0.01, that's really not very near 0. Cool, my code is awful. I should have taken less time on the pink buttons and more time on actually approximating integrals better. Oh, there it goes again. So even if I do a curve like this, I'm still getting back to about 0. Okay, let me show you what this one does. This one's a little bit different. Someone says, feels like we're about to create a black hole. So I'm going to go around both. There's 2 problematic points. Okay, so I'm going to go around both of them. And I get back, and that's just about 0. Someone said a Parker integral. Come on. It's about 0. It's pretty good. It's got 0.005. That's pretty much 0. Yeah, here we go. That's about 0. Oh, this is a little bit different. And so he's already thinking, Ross is thinking about a different function, x squared plus 1, which would have crosses at 1 and minus 1. Sorry, I and minus I. So it's a different function to think about. It appears that the problematic points, I like Zach's way of putting it, it appears the problematic points for this one have cancelled each other out. We go back to 0. And in fact, that doesn't matter on the kind of precise details of how we go around both, even if it goes over there. I wonder what it is over on the left. It's like some YouTube analytics thing or something that's just like borrowing my mouse occasionally. It's roughly 0. Here's an anonymous person says, and I love this question so much because you've completely predicted where I'm going with this. What if the loop goes through the crosses? Have I got a poll for this? Let's have a quick vote. Let's see what happens. Yeah, I think I made a poll for this. Yeah, okay. Let's see if people can guess. I kind of want to do the poll just to see what people will guess. I'm going to do that integral. I'm going to go from a, back to A, but I'm going to go between the crosses from above, in case that matters. Where are we going? What are we going to see? The way I like to think about this function, by the way, is it's a bit like you're exploring the world and everything's fine, except there's a kind of portal or magic mirror over here between these 2 points. We're going to find out what happens when you go through the portal. And then we're going to talk a little bit about portals. Voting is ongoing. People are voting. Oh yeah, computer explodes is one of the options in this one. Maybe the world on the other side has a better computer for me. Right. Oh, right, okay. There we go. Over on the left. Okay, let's do this properly. So we've seen that walking around, doing a little loop over here, it's fine, 0. Everything's integrated from A to A, you get 0. Doing a big loop around the magic mirror thing is fine. We're going to go through the magic mirror. So if I go between these points, I want you to watch the numbers. Nothing particularly special is happening as we go through. There's no sort of jump. There's no, bam, suddenly you're in a different world. As you go through, the numbers just change a little bit, as they do wherever you are, right? You're adding a little contribution, everything makes sense. When you get back to A, the integral is about 0 plus I pi, which is basically the least popular option in the poll, because I've kind of tricked you. I want you to see how weird that is, right? 3.1359, which we all know is the expansion of pi. So this is sort of weird. We've gone through the portal. I said I'd talk about portals. Some portals just sort of instantly transport you. You know, it looks like a shimmering mirror. You step through and it goes vroom, and you go through the portal and you're in a different place. Sometimes portals, I guess, in some sci-fi, like I think in the video game Portal, or I think kind of like Doctor Strange in the Avengers movies, the portal's more like just some regular space, and you step through it like stepping through a door. This is like that. This is like stepping through a door. There's nothing special about the door. The fact is just that you went through it. And somehow the integral, adding together these numbers, it can detect somehow that we went through between those 2 points. Going around, it gave us 0. Going through, I times pi. So Zach wants to do a loop just to test this out. You know, you've discovered a magic mirror. You've got to do some tests. Zach wants a loop that goes through the crosses, but without enclosing either of them. Okay. So that would be like doing. Oh, come on. That'd be like going over here. You're gonna go kind of through. Oops. And then left quite a lot. And then, but you don't want to cross them, so you don't want to enclose them. In that case, I get basically 0. So if I don't enclose the endpoints, that's a bit like going through the mirror. And then I think by geometry, if I'm not going to enclose one of the crosses, then I've got to come back again. So there's no quick transition point where it feels like you're in a different world. You just sort of amble through and amble back again. 0. Okay. This episode is going to need a lot of further reading. Yeah, okay. I'm going to try and explain what's going on after a break. Right, okay. So we've seen some weird stuff. We've seen a function that feels like you're going through a magic mirror. Feels like things are being a bit weird. Let's end this. Use of the end button. And restart this. Okay. I'm going to try and give you some closure on what's going on. So there are some weird points for these integrals. They were red on the stream, weren't they? Red on the system. And the integral that we saw, this is kind of the theory of everything we saw together, was if you go around one of these, then you get a contribution, which at first we saw maybe it was 2 pi I from that one for f of x is 1 over x. And then later we saw one where the contribution was kind of, if you went around one of them, it was a bit like getting pi times I. Have I drawn that arrow the right way? Maybe I have, maybe I haven't. That was for a different function. So it sort of depends on your function, what you're going to see, and it also depends on, you know, if I went around that one, then I get one thing. If I go around both of them, so for this second function that we saw, if I go around both of them, then somehow that was 0, which is sort of a bit like, if I'd had time I would have just tested out the left-hand one. That's sort of like a plus pi I from this one, and a minus pi I from this one. Somebody said they cancel out. So it's like the things cancelling out. Oh, somebody wanted an infinity symbol. Oh, that's a really good idea. We could do an infinity symbol if we've got time at the end. Okay. Well, maybe I'll tell you about what should happen for the infinity symbol. So my prediction for an infinity symbol, he says, I'll do it at the end, he says, and then instantly starts talking about it. Okay, here's the theory for the infinity symbol thing. If my theory is correct about contributions from the problematic points, that the kind of fine details of your path don't matter, but it's just the contributions inside, then this infinity symbol would have, well, so it's going to have a contribution from going around this one that I think should be like pi I, and it should have a contribution. This one, it was normally minus I pi, but we're going in the other direction. So I think that should also be another pi I. So maybe this will be 2 pi I going around in the infinity sign. And this theory's got a name, so something we do on a university course is called complex analysis. And we look at integrals like this, where the brilliant theory is, if your function's nice, if it's differentiable, then it doesn't matter too much about the path, the shape of the path. You don't have to use a straight line. You can use any path you like. The integral that you get from doing a closed curve thing, a to a, back again, it is not 0. It depends on these problematic points inside, just the ones that are inside your curve. The theory looks like this. I'm going to show you the theory because I want to put some complicated maths on the screen. We've got about 10 minutes to go, so got to show off some maths. It's called Cauchy's residue theorem. It says the integral of a nice complex function around a closed curve. So around a closed curve, we're going around some sort of closed curve, but it doesn't matter. It doesn't have to be a circle. It just depends on the behaviour at poles, which are essentially just points where your function's not defined, or points where your function would be infinity if you try to define it there. The formula is brilliant. It looks like this. I just want to point at bits of it very quickly. So this is in a sort of second year complex analysis course or something. There's this cool notation for doing, if you're doing a whole loop around, if your curve gamma, so this is your curve gamma, if it goes all the way around, then people put this kind of loop on the integral sign to remind you it's a loop that goes all the way around. That's nice. And it's equal to, there's a factor of 2 pi I, which is really nice. And then there's sums. So there's lots of contributions that you need to add together. Well, maybe not lots. Ones where you've got some problematic contribution. There's a term for the residue. So this bit is called the residue. And it's something to do with how bad is your function at that point. How bad is your function f at that point. And there's this contribution I that's called a winding number. And it counts how many times did you go around. Isn't that mad? Isn't my handwriting bad? So this is pretty weird. It is, as E says, it's topology-ish in the way that it connects things together. There's a topology way to imagine that thing I said about magic mirrors and going through to parallel dimensions or whatever feels a little bit topology-like. You're not exploring like an argon diagram, you're exploring something with a more complicated topology. So there's a link. Alice says, there is a relationship between the argument and the value of the integral. Yes, I suppose it's the argument of the integrand that is giving. Yeah, there's a link. I'm going to do it after a quick break. So points where it's bad are, yeah, essentially if your function looks like, I don't really want to define pole. Okay, it's a cool formula. It's got lots of Greek letters and lots of sums in it. Really, it's just trying to explain the thing that we just observed, that the number of times you go around matters. You know, like that time we went around twice, it was 4 pi I. That would be like having a winding number of 2 about that red cross. Point AK here is just where is your red cross? Where is your pole? Okay, and the residue is something to do with what's going on at that function. Okay, right, I've got a quick ad break. I want to add some numbers together, kind of unrelated. Rose says, what's topology? Rose, we did great news. We did a past episode about topology. It's the study of properties of shapes and surfaces, sort of. So looking at which surfaces are sort of the same under transformations. So at school you learn about kind of regular transformations like translations and stretching. And you can use those to move objects around and change their size. At university we look at some other transformations you can do on shapes, sort of anything you can do by stretching an elastic or kind of stretching a kind of rubber surface. So like taking a sphere and stretching it out into an ellipsoid, or doing some complicated twisty thing. Any of those transformations, which surfaces end up looking kind of the same. Ad break, here we go. Okay. So the ad break is our chance here to have an ad. There's no poll for it, but yeah, people have got some answers here. Some people are saying that this should probably be 2 pi I. Some people are like, oh, interesting. Partial fractions. Yeah, partial fractions. Someone's giving you closure. Okay, very quickly. If you're watching the playback, pause now for a tiny text explanation of why it was I pi, not 2 pi I the second time. There's secretly a factor of 1/2 hiding in the second function. Those people are saying 0. Interesting. Okay. There's approved loads of people saying 0. That's my engagement metrics up if loads of people say 0. Okay, I kind of get the logic for 0, right? That the logic for 0 here is that this is something like log of I times I times I times I, which would be log of, well, I to the 4 would be 1, so this would be 0. But hang on a minute, because this is also 4 times logarithm of I. Somebody said that quite early on. So if 4 times logarithm of I is equal to 0, so is logarithm I equal to 0? Seems a bit weird. The logarithm of I should be equal to 0. Logarithms are weird. In this last sort of 10 minutes, I'd just like to convince you that logarithms are weird. So really the ad break, before adding these things together, someone should have asked me, what does log I mean? What is log I? There's a reason you only put positive real numbers into logarithms at school. Let's find out. Okay, logarithms are weird. A 5-minute maths talk from the University of Oxford. Logarithms are weird. You know complex numbers? You'd sometimes write them as a plus ib. Yeah? Yeah, Ali says 0 feels wrong. Ali, I think you're right to this feels wrong. Doesn't feel right? It doesn't feel good to have log ib 0. Yeah, it's pretty bad. No one likes that. Yeah, people didn't like that. Right. 5-minute outreach talk from the University of Oxford. Logarithms are weird, yo. Z, if you sometimes write your complex numbers like z equals a plus ib, sometimes you write them like r e to the I theta. Okay, that's pretty standard. Like, I think further maths will teach you both ways to write complex numbers. If I want to do a logarithm of my complex number, then I'd have to write down something like, well, log z. I haven't put a base on my logarithms. Am I going to get in trouble for that? I hope not. All my logarithms are base e. They're natural logarithms, I suppose. Maybe I should be writing ln. I'm really sorry. Okay, so I'm going to do my natural logarithms of both sides. And I could use log rules to write that as log r plus log e d I theta. Log of a product is equal to log of each of those parts. And then log e to the I theta, I'm using base e. I should really have written down my base e. I'm using base e, so that should be I theta. Okay, brilliant. So there you go. I've got a nice formula. If you give me a complex number, I've got a nice formula for my logarithm. This is sort of the only thing that makes sense, because it's the only thing that's consistent with that way of writing down my complex numbers and rules of logarithms for writing things down. But hang on. Theta isn't uniquely defined for a point a plus ib. When you write down the argument of a complex number, which I think is something Rose said earlier, the argument of a complex number, you've got some choices. you could choose theta to always be between minus pi and pi. Some people write their complex numbers like that, to have arguments between minus pi and pi. Some people write their arguments between 0 and 2 pi. So do those people have different logarithms? Sort of, yes. Some people write their logarithms so that the angles theta are between 2 pi and 4 pi. Those people are weird, but logarithms are weird. So those people with their different definition of theta, sort of doesn't matter really for what the complex number is, but then when you do the logarithm, feels like it matters. Turns up in that theta. So yeah, okay. So that's kind of weird. That's the end of this 5-minute logarithms are weird, yo. Outreach talk from mathematics at Oxford. The way round this is to say, well, you know. So I guess one consequence of this is that if I'm trying to define my logarithm function, so I can have my logarithm function be nice and continuous over here. So over here I've got my over here in the Argand diagram, you know, over here I've got my real numbers. I know what I want to do for logarithm of those, and then if I start going around here, if I start going around this way, well, that's fine. So I could say theta is some angle between 0 and pi by 2. Okay, that's not controversial. I'll get round here, and up here I'll say, well, these are a bit like, you know, they're sort of log r plus I pi by 2. That feels kind of sensible. Everything's nice and continuous. And I can keep going round. As I go round, I'll get over here, and hey, I get to define logarithm of some negative numbers. I'm going to say that that's log of r, log of the absolute value, plus I pi. Hey, maybe that's why they don't teach you about logarithm of negative numbers at school, because it involves complex numbers, sort of. Okay, all very nice. As I keep going round, I'll get over here, and I'll keep going around, and I'll say that these ones are like log r plus 3i pi over 2. But then when I get back again, just before I get back to the real line, I'll be looking at saying these are log r plus 2i pi. And that's inconsistent. Oh, I'm off the screen. Not being consistent with my screen. That's inconsistent because I've got back to the real numbers, and I'm not saying the same number for logarithm. So this is sort of the same problem that we had with our integration before. That if you stay in a little patch nearby, you can define a logarithm nicely. You can define your logarithm of complex numbers, and everything makes sense. But if you walk all the way around the origin, then when you get back, things are different by a factor of 2 pi. So that's logarithms are weird. Defining logarithms in the complex plane, you've got to be really careful. Rose says, is this a topic in Oxford Maths? Yes! This is a topic in any maths degree you do, I hope. This is called complex analysis. So complex analysis looks at functions that have complex inputs and complex outputs. So it takes functions, which we know and like, and it looks at complex inputs and outputs, and it looks at the consequences of that. That kind of experimentation that we've been doing today to look at the consequences of what happens if you integrate along a strange curve in contour in the plane in the Argand diagram. There's some weird consequences that come up, like Cauchy's residue theorem of having these contributions. Just to tie it together, in the last 2 minutes, this is for the enthusiasts. We've been doing the integral of 1 over z dz around a curve. If you try and do that integral of 1 over z dz, then you find that you kind of get logarithm of z around your curve, which is then going to differ if you go around the origin. If you go around the origin, that's going to be different by a factor of 2 pi I. So this 2 pi I in the logarithm thing is the same as the 2 pi I in the Cauchy residue theorem. The poles are kind of bits where your function looks like 1 over z. Which is why we tried 1 over z earlier. Not everybody knows that the integral of 1 over x is log x. So this is enthusiasts only. Right, okay, there we go. Cool, right, I'm going to wrap up there. Is it because 0 is undefined? 0 is a big problem in this. Yes, sort of. There's a big problem at 0. which is again to do with the kind of topology of the space. The topology of the Argand diagram is very different from the topology of the Argand diagram without the origin. If you just take away the origin, then almost everything is the same, but the topology is not the same, because now there are loops that you can't transform, make them transform elastically to a point. Oh yeah, this would make more sense if you knew that z equals re to the I theta. I guess we all learnt some maths today. There's this way of writing complex numbers. Oh, by the way, e to the I pi is -1. Hooray. Okay, right, good. Is real analysis harder than complex analysis? Yes. I thought, well, complex analysis has got some really good results in. This thing about this thing is really good. It lets you essentially do tricky integrals. Real analysis is also hard. Do the log laws work with complex analysis? I guess the punchline is that you have to be really careful with your definition of logarithm, because when I showed you this addition problem, it's trying to trick you into going around the circle by going all the way around, by adding together log I, log I, log I, log I. So you keep going all the way around. So you have to be careful with what the arguments that you're putting into your logarithm are and what the outputs might be. Logarithms are weird, yo. Right. Okay, I'm going to wrap up the stream there. I'm going to hang out and chat a little bit because people are asking really good questions. I sort of want to explain, for the person who said I don't understand re to the I theta, I sort of want to explain what r and theta are, so I might go and explain that. It's polar coordinates. Do people know about polar coordinates? Okay, we're going to have a chat about polar coordinates and de Moivre's theorem in chat. Otherwise, thank you for joining us live or on the on-demand replay. Whether you're watching live on June 21 or you're watching at some other time, great to have you with us. We will see you again for another episode of the Oxford Online Maths Club in 167 hours. Have a great afternoon, have a great evening, wherever you're watching. Take care. Goodbye.